It's my pleasure to introduce the final speaker of this morning's session, Chevalley Property from Fudan University, and he's going to speak on the Chevalley Property and discriminant ideals of Hopf algebras with larger centers.
Thank you. First of all, I would like to set it all that yes, we invited me here. I'm very happy to be in Sofia. I will talk about mainly the irreducible representations of Hopf algebra with large centers, which includes lots of content groups at the roots of unity in DK sets. But I will do a uniform form in Hopf algebra with central sub-Hopf algebras. Which is also the big one is finite generated module over the small one. That this talk is based on the following works. In fact, this project was initiated by Ian. Yeah. And we don't have this here. And some other people are my students. And then first I will give a quick review about Chevalley property. And then I will give you a general framework about kind of how the Hopf algebras to work for the irreducible representations. Finally, I will use discriminant ideas to characterize Chevalley property. A classical theory about Chevalley in 1950 says the tensor product of any finite-dimensional irreducible representations over group algebra or envelope algebras is completely reducible. After that, people call this property the Chevalley property. That means a Hopf algebra actually set to have the Chevalley property. If the tensor product of any two finite-dimensional reducible modules is completely reducible. And in fact, for finite-dimensional Hopf algebras, it was proven in 1981 by Moller. The following are equivalent H at Chevalley property. The Jefferson article of H is a Hopf ideal of H. And also, which is equal to the co-radical of the dual of H, is a Hopf subalgebra of the dual. So, any finite dimensional semi-simple Hopf algebra has the property because of the value is 0. And any finite dimensional base Hopf algebra, because the dual is pointing, so the co-radical of the dual is a subalgebra. So any finite dimensional base Hopf algebra also have this property. Of course, there's an example of finite dimensional Hopf algebra have the Chevalley property, which neither semi-simple or basic. The middle one is the 16-dimensional one.
So what is basic Hopf algebra?
Basic algebra, okay, only one isomorphism class of simple isomorphism class for each one. Only one simple components. That means in characteristic theory case, that means modulus the Jefferson article is K. So product of K. Yeah. Yeah. And the small quantum groups at the roots of a unit because it is basic. So it has a Chevalley property. the quantum group UQG, because it was proved by Russell, any finite dimensional representations on UQG is in fact completely reducible. So it is a Chevalley property. For the other two, because every finite dimensional irreducible modules are one-dimensional. So they have Chevalley property. Of course, it is Q should be not a root of unit. And it is also proved by Mola in the 1981 paper. If the characteristic of the field case P, and G is a finite group, then the group algebra is a Chevalley property. If and only if G, the P single group is Rome, the Rome subgroup. There's only one P single group subgroup. And for any restricted algebra, that is restricted the enveloping enveloping algebra, that's a Chevalley property. If only if the general symmetrical portrait is generated by it's generated by P potent of G. And the ethical clarity also proved all finite dimensional triangular Hopf algebra over algebraically closed field of characteristic theory. Over the Chevalley property. And because well, we say tensor calculus have the Chevalley property, the tensor product of any irreducible or simple object is completely reducible or semi-simple. So any finite symmetrical tensor category has the Chevalley property because finite symmetric tensor category is just the representation of finite triangular, the representation of finite triangular Hopf algebras. And there are finite dimensional quadratic triangular Hopf algebras without the Chevalley property. For example, the Lustig small quantum group. Also, we know a lot of Chevalley properties for finite dimensional Hopf algebras, but for the infinite number, we in fact we know it. So in my talk, I will work on field of characteristic theory, and which is also algebraically closed. And I call module finite algebra is a K algebra.
Sorry, I think I'll.
Yeah, I call K algebra is a module finite if you had a central subalgebra over which A is a finite again. And that's the not speaking, module finite algebras with big centers around 7. And I use letter A to be the isomorphic class of all irreducible modules. In fact, any module finite algebra is a PI algebra, and I will use the fact the Kaplanski theorem, any primitive PIV is a central symbol algebra. That means a finite dimensional algebra over its center. So for any that may be a module finite algebra.
Can you show the previous one? To the previous one, show.
Previous slide.
So AR, so what is R?
R is the central subalgebra.
What?
Central subalgebra.
Central. And then you have n only x1 through xn, but you are running over Sn plus 1. What does that mean?
Yeah, you with this identity. Let's
No, but there are only n xh and there are n plus 1.
Yes, here is this is determinant by this is ruled by P.G. principle. That means for any finite model finite algebra generated by m element satisfies this identity.
Oh, I see. For any n plus 1 elements.
Yeah.
Well, I see. I don't know. Yeah. But
So for any irreducible representations, if we take the element, it's a primitive idea. But in our case, model the primitive idea is a PIV. So this is the central symbol algebra. And also it's only one isomorphic class. So we have a one-to-one class between the irreducible representation of A and the primitive ideas of A. That's one-to-one correspondence by Kaplanski theorem. And also by Kaplanski theorem, any primitive idea is a maximal idea of A. And because A is finite generated over R, then the maximal idea descends to the maximal idea of R. So we get the surjective map here. So all the way, then we get the surjective map here. And then so for any maximum idea here, M, the fiber is just the irreducible modules annihilated by M. So it's a irreducible representation of this algebra. So we call this algebra is a fiber algebra. This is a finite dimension. So in this way, the irreducible representations of A is a disjointed union of the irreducible representations of these fiber algebras. So we can just discuss the irreducible representations of over these finite dimensional algebras. So let me give us several examples. For example, for quantum polynomial algebra, the QIG, the OKA, the quantum polynomial algebra is a module finite algebra of its center. If the only is QIG are roots of unit, And for UQSL2, if Q is a primitive root, else root of unit, then in fact, then UQSLK is a central subalgebra R, which is in fact a polynomial ring. And UQSL2 is free with a basis in here, it's free module. But this one is usually a central symbol algebra, will not be a central subset of algebra.
But this is true for arbitrary G, right? This is right.
Yeah,
Why only you are taking a set 2?
yeah, I just give an example.
Oh, I see. Yeah. But it's true for any.
Yeah. And for OQG, then there is a central simple Hopf algebra, sample Hopf algebra, the isomorphic to OG. So OG is a Hopf algebra, finite generated over a central simple, central sample Hopf algebra, OG, and which is also finite generated at a finite generated projective module over H. So this talk, as I said before, will focus on the irreducible representations from tensor categorical point of view or discriminant ideals. And yeah, my major examples are many bigger quantum groups at the roots of unity at DK sets, and also many artificial stuff of no DK dimension. So here's the definition of trace. Let A be R algebra. R is a commuter ring. And R linear map from A to R is for the trace. If FAB equal to FBA. So the classical trace of a matrix, of course, is a trace. So in fact, there are maybe no non-trivial trace on some algebra. For example, if we take the first wire algebra, then every element in wire algebra is 4. It will have at least is the basis. So any monomial is in fact a commutator like this. But because the trace acting on the commutator is 0. So over this algebra, there's no non-zero trace function. But if A is a finite general free volume over R, if we take the endowed of A, then this is the isomorphic to the matrix screen, then there's a class check. I think they're touching.
No. I don't think it's supposed to touch. I think we can just restart it. Yeah, sorry.
So if we take a finite general free R module, then we consider the endowed is a matrix group. That's a classical shape. And then if we take the left multiplications, there's a zero homomorphism from A to the multiplicity of the projective module. So the concentration will give us trace. In fact, if we reduce to the finite field extension case, that's the trace in power theory or number theory. That's the case. And in general, if the module is just a finite generated,
Restart the computer. Restart the computer? Yes.
Okay. If we start from a finite general free module, then we get a trace before the negative trace. And if we start from a finite generated projective module, then we can also construct a trace. And using the pure basis lemma of the finite projective module, we call this trace.
Should we change the computer?
It's a Hattori-Stalling trace. Okay. So for finite generated projective module, we can introduce the algebra a trace, non-trivial trace. Okay. Now if we consider Hopf algebra, with central subalgebra algebra. Then usually the big one is a facial flat module over the small one. But if we consider the Hopf algebra is affine, is generated by finite element, so Hopf as an algebra, then it will be finite generated projective. Finite generated projective. Then so we can endow with such kind of Hopf algebra with the checks, the so-called Hattori-Stalling checks. Yeah. Yeah, that's for finite generated projective modules.
Just a second.
Yeah,
I think it's better.
maybe I ask you this let's indicate that the model to the tensor factor the one of P and P. Yeah, this is isomorphism. And this is the evaluation map. You can match it and what you know.
Maybe if you stand on the other side, you.
The other side, okay. Yeah, then it is easy to check by the pure basic dilemma.
It came back.
Okay. And this is a will give a chase map. So
That now I think it's something with button.
okay. So if A is not only finite generated but also finite generated R projective modules, then we can also get the chase map
And it's algebra or a module?
as a module. This time AR is finite generated projective module
An R module.
as an R module and an R module. Yeah. Then this is a long-term chase. We call it it is a Hattori-Stalling chase. In fact, many chases are derived from this chase. And if we have a chase, for example, in finite field extension case, or the generator A is a finite generated ring module over R with a basis x minus 2xn, then we can define the discriminant. Just in the finite field extension. That means we put the xi. Okay. Put the negative trace of xi in the ideal position, we get the matrix.
Wait. So what?
Just stay there and check cables.
Watching the screen, it's a touch screen, so the AC could be causing this.
Ah, yeah. Let's turn
Well,
off.
they don't for all day.
Yeah.
Okay.
Just turn it off. It's not.
So if we take the determinant of each matrix, that's the determinant of A over R with the chase, with respect to the chase. And the chase, the discriminant is unique up to a scale, non-zero scale, non-zero invertible scale is a ring. And in general, if we have a chase, then A may not be finite generated projective or something. That's we have a chase. And if R is a central subalgebra, then we can define a series, so-called M discriminant ideal for any positive integer n. In fact, the discriminant idea, M's discriminant idea is generated by all these kind of determinant. This belongs to for any vectors of in M. And then in fact, this is all these determinants is in R in the second simple algebra. So this is ideal in R, generated in R.
So this trace function, you don't require some non-degeneracy condition?
No, because for example, for Hattori-Stalling, well, as I said, it's non-zero.
Sorry?
Non-zero is not zero. We don't need non-degenerate.
You don't require non-degenerate.
Yeah, if you give that network, you can some property extension or something. So, and James and his partner also defined so-called modified M discriminant ideas, right? They just replace one vector to two vectors. Then we get a modified determinant. And if R is free, go back to free case. Then in fact, if the basis consists of n elements, then the n's determinant idea and the n's modified determinant idea is just the idea generated by the determinant. And in general, we have a descending chain of the modified determinant ideas. And also in general, the determinant idea, of course, belongs to the modified determinant idea. So if A, you put the A is affine, the generated finite generated algebra, and also A is finite generated module over R, then the zero set of these two ideas are the same. And we call Vm is the M's determinant variety of A. And of course, we have the chain of the closed subset over the maximal spectrum of R. The first line is empty. And because I assume A is finite, is modular finite over R, then for some big N, and the determinant idea will be zero. So the determinant variety will be the whole space. So we have someone will be the whole space, and we take such an N, and we call the corresponding determinant idea is the highest determinant idea. And on the other hand, because V1 is always zero, because the determinant idea of fourth degree is the whole ring. So we have this empty, and we take the first non-empty one to be to call this as the lowest determinant variety, and call the corresponding determinant idea to be the lowest determinant idea. Okay, so now let me remind you. So for the Cayley-Hamilton algebra or Cayley-Hamilton Hopf algebra, and if M is a matrix ring, then we have the characteristic polynomial, and M satisfies this characteristic idea, this polynomial idea. And if the R is algebra closed field, then we know the coefficients of this is just the elementary functions of the eigenvalues. For example, this one is number 1 plus number 2 plus the n. But in general, the coefficients in community gates, we can compute the coefficients here by the chase of m, the chase of m squared, chase of mk. So if we have an abstract chase, then we can also define for any element A. We can also formally define characteristic polynomial like this. We just replace, we just define CKA. Here, just replace chase M to chase A squared, chase AK. So we get a formal polynomial. And if for any A satisfies the formal polynomial and the chase of the identities N, then we call this algebra is Cayley-Hamilton algebra. This, in fact, this is defined by the Concini-Procesi. And any affine Cayley-Hamilton Hopf is in fact a module finite algebra, because in fact any affine, any Cayley-Hamilton Hopf algebra can be embedded in a matrix ring as a subring over commutative algebra. So it is PI, it's a PI ring. And then if any small element satisfies polynomial, there's something like integral extension. So if PI and every member is an integral element, and then if the element is affine, then we know the big algebra is finitely generated over the small algebra. Then by architecture lambda, we know the central subalgebra R is affine. There's no Gaussian, we can also get a Gaussian. And we will use SD, the function for the max spectrum R to N. That means M maps to the summation of the dimension of square of the dimension of V, where we answer over all irreducible representations over MA. And there's a very deep result belongs to Brown and Yakimov. They proved that if AR with the chase I is an affine Cayley-Hamilton algebra of degree n, then for any positive integers k, the case discriminant variety is considered of all such kind of maximum ideal n, such that the SDN is less than k. So they relate the discriminant variety with the maximum ideal. So, and then we call a Cayley-Hamilton Hopf algebra. It's just the Hopf algebra with a central sub-Hopf algebra and the chips such that this triple is a Cayley-Hamilton algebra. And for example, if we take the infinite dihedral group, and the group algebra is a modular finite algebra, we can find the big center. But it will not be a modular finite Hopf algebra. We cannot find the big Hopf center, Hopf subalgebra. And by using the result, form result of James, because as I said, any Cayley-Hamilton Hopf algebra is PI, no ceiling. So any Cayley-Hamilton Hopf algebra are Gronsky. That means they will have a finite injective dimension. Then we can define homological integral. Just like the infinite dimension case, we have integral and the irreducible this. And Because I assume case algebra is closed. So for any affine algebra, if it is modular finite algebra over set subalgebra affine R, then the maximum ideal of R is in one-to-one correspondence with the characters from R to K. From R to K. If you have a character, you just take the corner, of the character. And in this case, in fact, this is algebra group, and because we work on a field of current district zero, and in fact, this affine group and it's smooth. After it is smooth, so we will use this fact. And for any two characters, and for the time and phi, time, and the product of time and phi in the group, they corresponding to a maximum ideal. So the delta will map to this one, maximum ideal to this one, and this will induce the delta will induce algebra morphism from this fiber algebra to this the product, the tensor product of these two fiber product. So if we take this bar to be the unit of R of H is restricted to R, then in fact this bar is the unit of in the algebra group. So we have for any character we have this one. So if we take both this bar is identity. So this will tell us this fiber algebra is a finite dimensional Hopf algebra. Yeah. By this. And for any other fiber algebra, by using this algebra map, and there will be co-modular algebra over this one. We call this one the identity fiber algebra. Identity fiber algebra. So any fiber algebra is left and right co-modular algebra over the Hopf algebra. Is an identity fiber algebra. And in fact, the fiber algebra is a bidirectional object. Bidirectional object. And okay, maybe I skip it.
You were
Well, more than 12 minutes.
20 minutes because you were interrupted. 20 minutes. You had long.
Because our Hopf algebra now is PI. No student PI. So the antipode is bijective by this result of similarity. Then that will give us the left dual or the right dual. And this one will give us tensor category. That means the finite representation of the identifiable algebra is a tensor category. And any the finite representations over any fiber algebra is in fact indecomposable exact model category over this one. So by using the tensor category theory, we can prove by using tensor category we can prove if H is an alpha Hopf algebra, which is a modular finite algebra over essential sum of algebra, then as I said, then HR is a finite projective module OR, and it will have a constant rank. That means at any the normalization at any maximum ideal have the same rank as the free module. Then if we introduce it with a Hattori-Stalling phase, then with this Hattori phase, it will be Cayley-Hamilton Hopf. So So alpha Hopf algebra, which is model finite algebra over central Hopf subalgebra, is equal to say HR is an affine finite Hopf algebra in some sense. But when we consider the determinant, we can use not only the kind of Hattori-Stalling trace, but we can do maybe some other trace.
Where do you use that it was a Hopf algebra as opposed to just algebra?
Okay, but if we cannot get this one, we can go to this one because if the big Hopf algebra has such a sub Hopf algebra, then it will be basically flat. But if we add that Gaussian condition, then it will project it. So in application, we will not get it. So yeah. For then I would want to distinguish color half alpha color half in the Hopf algebra. Oh, so if the identified algebra is simple, then actually we'll have the Hopf algebra will have Chevalley property. So if we start from a Hopf algebra, which is evolutively relative S square is identity, then this one will be simple. So actually we are Chevalley property. So any commutable or co-commutable such kind of algebra will have kind of Hopf property. And for such kind of Hopf algebra, if the identified has Chevalley property, then we can describe the most discriminant ideal. The level is just the Frobenius-Perron dimension of this growth degree plus one. And we can also describe the lowest discriminant variety for such M. So from this one, if H has a Chevalley property, then all this will be completely reducible. Then that means all maximum idea of R will belong to lowest variety. That means if H has a Chevalley property, then all the discriminant idea will be trivial, either zero or the big item. So for such kind of algebra, if H is, I assume if H is prime, then H has a Chevalley property, then all the discriminant ideas will be trivial, and the square dimension will be constant, and all the five algebras are semi-simple, and this is equal to the identity five algebras semi-simple. But this is also equal to H is commutative, because this is a prime ring. So this will give us quantum envelope algebras at the root of unity, or quantum chaotic algebras at the root of unity, or quantum polar subalgebra at the root of unity will not have the Chevalley property because they are not commutative. But as I said in the photos second page, in fact, the quantum envelope algebra for this kind of the non-unit of roots, where we will have the Chevalley property. And I will introduce another concept. We call H what V is left tensor reducible. If V tensor any other irreducible module W becomes to completely reducible. And we can, in the same way, we can define the right reducible modules, or tensor reducible means left at the right reducible. And because then we can prove any tensor reducible module, in fact, is completely reducible, because this one is reducible, it's isomorphic to that. So, and all one-dimensional H modulus are tensor reducible. So, in fact, any affine module find a whole pattern at Chevalley property, if and only if all irreducible modules are less than tensor reducible. That's why we want to introduce this. So suppose we have an affine parallel algebra, and the identified algebra of this property. Then for any other irreducible H module V, then V is less than tensor reducible is equal to V is right tensor irreducible, or they are both on both sides tensor reducible. And this is equivalent to the modular irreducible module V is annihilated by the lowest discriminant, or annihilated by the lowest modified discriminant. And this is also equal to V tensor of the left dual of V is reducible. So, yes, it was very much this. So then we get, if HR with the trace is affine Cayley-Hamilton Hopf, then the following are equivalent. H, the Hopf and the Chevalley property. The identity fiber algebra at the Chevalley property, and the lowest discriminant ideal is 0. And which is also equivalent to the fiber algebra, identity fiber algebra at the Chevalley property. And the lowest modified discriminant ideal is 0. And which is also equivalent to, in fact, equivalent to the identity fiber at the Chevalley property. And the discriminant ideal, the series is just to one, either 0 or either the whole ring. So that's the description of the Chevalley property. In fact, I want to say the identity fiber algebra controls, in some sense, controls the property of the whole algebra. And if we want to consider the remote property or Cayley-Hamilton property, it's all controlled by this one. And okay, let's just if the following are equivalent, actually at the Chevalley property and actually at the finite block dimension, then this is equal to actually 75, which is for many numbers 75 at the actually at the Chevalley property, and which is equivalent to all the fiber algebras are semi-simple. All the fiber algebras are semi, all the identity fiber is semi-simple. Okay, maybe I stop here. That seems it's applied to some group. I assume. Thank you.
Very much. Questions?
So for the theorem that the last on the second group last was, you don't actually have additional conditions for H or R ones.
You suggest.
Yes, it is for just any H R.
And the TI.
I see.
Yeah, so the next slide, when you say semi-prime case, I remember in the prime case, you get H. In this case, you don't get it.
No. That's we just assume. Okay. Yeah, it's identity fiber that and also this one. Yeah. This one I don't know.
Can you show us the applications for quantum groups?
We'll check some examples.
Mhm.
Okay.
Mhm.
For this one,
Mhm.
then I should just show the degree to chase something.
Mhm.
Then I just show this is in fact
Mhm.
very small quantum groups
Mhm.
are the fiber are the identity fiber
Mhm.
of the
Mhm.
bigger quantum groups.
Mhm.
Yeah.
Mhm. Mhm.
Let's just check that.
No, that's not the case. As